Alright guys, this is extension 2.7. Our goal here in this section is going to be able to evaluate, graph, and write piecewise functions. So a piecewise function is a function defined by at least two equations, each of which applies to a different part of the function's domain. So remember, domain is all your x values, so it makes sense to see if you have a certain x value, then you're going to look at separate equations to get your y value or range of outputs. So the equation y equals 2x minus 1 gives the value of g of x when x is less than or equal to 1. The equation y equals 3x plus 1 gives the value of g of x when x is greater than 1. So for example, it says evaluate the given function when x equals 1. So your domain here is when x equals 1. Well, if I look back in my original equation here, or equations, my domain is restricted to being less than or equal to 1, or if I'm greater than 1. Well, this says equal to, so I'm going to use this first one. So, I'm taking g of x, but I'm plugging 1 into it, so g of 1. And I use that first equation. And instead of x, I'm plugging 1 into it. Well, 2 times 1 is 2, minus 1, well, it just gives me 1. Evaluate it all the way down. This says, okay, evaluate the given function when x is 5. So 5 is bigger or greater than 1, so I'm going to use that bottom equation. So if I use g of 5, because I'm plugging 5 in for x, I need 3 times 5 plus 1. Well, 3 times 5 is 15, and if I add 1 to it, it will evaluate it all the way down, gives me 16. So basically what you need to do is just make sure you line up what your x value is and compare it to your piecewise function of your restricted domains. Alright, in example 2, we're going to actually try to graph it now. Okay, so we're trying to graph the following function. So that first one says if your x or domain is less than negative 2, so it doesn't quite include negative 2, it's going to follow negative 3 halves x minus 1. So everything from negative infinity to negative 2, if you want to write it in interval notation, because it doesn't include negative 2, it gets parentheses. Then, from negative 2 to 1, it's exactly going to have those values, negative 2 and 1. So we're going to use x plus 1 as the value there. Then everything bigger than 1, so it doesn't include 1, and all the way to infinity that's bigger than 1, it's just going to be straight up 3. Okay, so if I try to graph this first one for anything less than negative 2, okay, so if you try to plug in negative 3 in there, so negative 3 halves of negative 3 minus 1 is 7 halves, or it's the same thing as 3 1/2. So you plugged in 3, or negative 3, excuse me, and got back 3.5 or 3 1/2. So negative 3, 3 1/2. Okay, and if you try to plug in 4, negative 4, excuse me, negative 3 halves times negative 4 minus 1 gives you back straight up 5. So negative 4, 5. Okay, so this is going in this direction since it's a negative slope. But if you try to plug in negative 2 for that first equation, okay, you're going to get back out positive 2. So at negative 2, we're supposed to get back out 2. Okay, but what I'm going to do is leave an open dot at 2. Okay, because it doesn't quite include 2. That's why I have this in interval notation here. Okay, it didn't quite include -2. That's why I didn't have the half an equal sign underneath. So I need that open dot there. But I need it to connect with the -3, 3.5 point there, because there's still numbers less than -2. So like -2.5, -2.1, okay? It just approaches -2, but doesn't really equal -2 there, okay? So now I look at this next equation. So if I plug, okay, at -2 at this middle equation, if I plug -2 in for x, -2 plus 1 gives you back -1, so I can graph that, -2, -1. And I'm going to use a closed dot on that because it included -2. And then if I plug in 0, I get back out 1. And I actually skipped -1, so let me plug that in. -1 plus 1 is 0. And then +1, because it still can equal 1, I'll get back out 2. And I can connect these because you can have anything in between -2 and 1, including -2 and 1. Okay, so there's the red part. Then it says anything bigger than 1, it's just straight up 3. So if I plug 2 in, it's still going to be 3. If I plug 3 in, it's still going to be 3. If x is 4, it's still going to be 3, and on and on and on. So 2 is 3. At 3, it's 3. It's 4, it's 3. 5, it's 3. Okay, it's going to keep going and going and going forever and ever. Okay. But at 1, if we were to try to plug in 1 there, it would be 3, right? So I'm going to use an open dot there too. But notice, I'm going to connect that open dot with the closed dots that are green, because you can have in between 1 and 2. So 1.5. That would be green, or 3, because 1.5 is still bigger than 1. Okay, so see how in blue it gets all the way down to 2, but it has to jump down to the red one because it didn't quite include -2. And then we did that red line all the way up to 1, 2, but it didn't quite include 2. Okay, it had to jump from 2 to 3 because these are piecewise functions. They're in pieces. Okay, so if you look, okay, if you remember from the first 2.1 extension, this is discrete, not a continuous function, because I have to break it up in points, right? It's not one continuous line, so it can't be continuous. So a stem function is a certain type of piecewise function, and it's defined by a constant value over each part of its domain. Its graph resembles a series of stair steps. So these kind of look like steps. So for example 3, graph the following function. So if it's between 0, so it includes 0, but doesn't include 1, it's going to be 1. So I can graph that. So at 0, it's exactly 1. But if I go all the way to 1, I'm going to use an open dot because it doesn't quite include it. Okay, but it's going to be 2 if it includes 1, but doesn't quite include 2. Okay, so I'm at 1, and it's going to be at 2. So here's my closed dot. And it doesn't quite include 2, so I'm drawing my line that connects them though, because it can be numbers between 1 and 2. Then it's going to be 3 if it includes 2, but it doesn't quite include 3. So at 2, it's going to be closed dot on 3, because it includes 2, but it's at 3. Okay, but it's going to be an open dot at 3 because it doesn't quite include 3. So it's always going to look like this, closed dot and some kind of open dot going on, and it looks like steps, right? That's why it's called a step function.